Okay, I never record podcasts on preprints, but some topics are interesting enough and the authors are credible enough that I expect the paper will get published after the review process, and I will track this paper, in the coming months to see if anything majorly changed in the published version compared to the archived preprint that I'm taking. It's called Machine Learning for Climate Physics and Simulations. It's a very nice, detailed review kind of paper, and I'm just going to be brief, but still it'll be a long podcast, I suspect. So here they are saying we discuss the emerging advances and opportunities at the intersection of machine learning and climate physics, highlighting the use of ML techniques, including supervised, unsupervised, and equation discovery to accelerate climate knowledge discoveries and simulations. So already very heavy technical words about, supervised, unsupervised equation discovery and so on, which some of it we will learn along the way, but some expects that you have certain background in AI, ML, deep learning, and so on. We delineate two distinct yet complementary aspects: ML for climate physics and ML for climate simulations. While physics-free ML-based models such as ML-based weather forecasting have demonstrated success when data is abundant and stationary, the physics knowledge and interpretability of ML models becomes crucial in the small data and non-stationary regime to ensure generalizability. So I have podcasts already on how Google is doing forecasts, and obviously they are not accounting for the non-stationarity coming from, let's say, climate change. This is what they are talking about here. Given the absence of observations, the long-term future of climate falls into the small data regime. Therefore, ML for climate physics holds a critical role in addressing the challenges of ML for climate simulations. You emphasize the need for collaboration among climate physics, ML theory, and numerical analysis to achieve reliable ML-based models for climate applications, such as predictions and presumably for projections at some level, but at least decadal predictions should be possible, which Google has already tried, and now Nvidia and others, Microsoft, everybody is getting into this business because they see it as a business opportunity, obviously. Just some simple definitions we will read along the way. Model, of course, is a representation of the system to make predictions, and now we are combining first principles with physics-based, ML-based, or coupled, physics-based and ML-based coupled. Simulation, of course, is physics-based models solved numerically. For example, the general circulation model, GCM, is a climate simulation that solves the Navier-Stokes equations with some details about subgrid scale processes, which we'll touch upon here. Emulator in this article refers to a subset of models that fit the data, bypassing solving physics-based equations, and directly use data itself to find patterns and make emulations. ML-based emulators that fit the data with machine learning models, so deep neural network type things, bypassing solving physics-based equations. Again, neural networks which have some biases, as we will mention. These are function approximators. Here goes my throat again. Function approximators are parameterized by function operations and parameters gamma that are optimized to minimize a specific cost function L, specified cost function. If it doesn't make sense, don't worry, just try to get a gist of the story. Non-stationarity, of course, is when you have time-evolving statistical properties, most typically now coming from climate change, background changes, chronic changes. Subgrid scale parameterizations, as I mentioned in the GCM, a model to parameterize the relationship between resolved states as a function of the unresolved or subgrid state. Clouds, for example, we don't know how to do them and we don't resolve them, but we resolve the circulation, moisture loading, everything, and we start parameterizing the subgrid scale processes that are needed to form the clouds and especially form the rains, right? ML-based parameterization, subgrid scale parameterization represented by a mixed layer machine learning model rather than physics-based equations. Okay, what is the introduction with all that background? Machine learning has led to breakthroughs in various areas, from playing Go to text generated with large language models, which have become very common now, LLM, and more recently to weather forecasting. Different from Go and LLM, the language scientists use to understand different from Go and LLM, the language scientists use to understand and simulate weather and climate has been equations rooted in fundamental physics. Physics-based equations, often differential equations, are essential to simulate systems where direct observations are limited and noisy, and equations are non-linear, so you discretize them and put them on a grid and solve them on supercomputers and so on. Even more so for projections of future climates where data are altogether unavailable, because we are trying to see where we are headed into the future, so we make up scenarios and so on, as we will see. Recently, ML for an oceanographer is mixed layer, so I should just say ML instead of machine learning. ML has emerged as an alternative tool for predicting model, as well as improving predictive modeling, as well as improving the understanding of climate physics. For instance, physics-free ML models such as neural networks, which are universal approximators of functions and operators trained on data from observations or physics-based simulations, have demonstrated remarkable ability to perform accurate nowcasting, very close near real-time forecasting, with lead time of a few hours. Weather prediction with lead times of several days, and El Nino forecast with lead times of a year. If you don't know what El Nino is, I have lots of podcasts you can look up. It remains an open question if some of the strategies and successes in these short time predictions can be applied to improve climate projections, i.e. to estimate changes in the statistics of weather events, so return periods of heat waves or tropical cyclones, for example, but into the next decades, centuries, and beyond. So we want to extend the time scales. I'm jumping forward. Weather versus climate, there's non-stationarity issues. So success story of ML for prediction has been primarily showcased in weather forecasting, which is a short-term problem where you don't have to worry so much about non-stationarity. You initialize the models and integrate forward, followed by initial attempts started in 2019. By 2022-2023, ML weather models, often called emulators, achieve at a fraction of the computational cost similar or better forecast skills than state-of-the-art physics-based weather prediction models. So AI obviously can help improve models, but directly it can help to make predictions which with GCMs, for example, would take a long time, needing heavy computational resources, and they can be slow. If you want to make a 15-minute forecast, it may be nearly impossible with the model because it takes longer to integrate 15 models, but AI/ML can jump these hurdles and give you very computationally efficient and more skillful forecasts in some cases. Of course, this has generated excitement about ML to improve climate projections as well. Yet climate projections involve major additional challenges, not knowing many things and having to assume many things like population, GDPs, energy, transportation, buildings, policies, etc. In weather forecasting, we have a constant stream of real-time and historical data for training ML-based emulators to make predictions for a few weeks, where the statistics can be assumed to be stationary. In climate, we are often interested in predicting the climate's forced response to changes in greenhouse gases in the atmosphere, leading to non-stationarity. So the non-stationarity is we summarize the non-stationarity challenge and potential solutions, such as incorporating physics constraints, in section 2.2. Furthermore, the long-term predictions of future climate involves the interactions between the atmosphere, ocean, cryosphere, land, and biosphere, which make the problem more challenging than short-term weather forecasts. But more importantly, climate change projections also involve what we will do in terms of our policy and technology and other things. So here, looking at conceptual diagram of ML applications in climate sciences with respect to the availability of existing physics-based equations, availability of data, and interpretability. So availability of data and availability I'm not an English speaker, availability of physics-based equations. You have future climate needing data assimilation, inverse problems with the critical step, and you need, of course, subgrid scale parameterizations, equation discovery, which we will read in a minute, and supervised neural networks. So what data can actually help us with, and interpretability here versus availability of data. Again, you will need data assimilation and inverse problems. Basically, inverse problems are where you take the data and try to derive something that is constrained by what we have data for. Okay, so flux calculations or transports of ocean across a certain latitude, having just temperature and salinity data, and so on and so forth. So you can look it up if you wish. Okay, so equation discovery, subgrid scale parameterization, and supervised networks now going in this direction in terms of increasing availability of data and the applications for interpretability. Okay, so you can look up what interpretability is. Existing physics-based equations and data are two sources of information used for ML models. More physics-based equations are not necessarily more interpretable. For example, existing numerical weather predictions. On the other hand, equation discovery usually comes with regularization techniques to find the simplest set of equations capturing the dominant behavior of the system, enhancing interpretability. So they have another article, okay, they are not for editors, but they use the Lorenz model here, the Lorenz chaos model, which is very famous. If you don't know, don't worry about it. And they use that to make some of these points about interpretability, availability of data, and so on. What are the challenges in understanding and simulating climate? Climate system consists of obviously interacting processes that span orders of magnitudes. Simulating climate system to resolve all these scales is computationally challenging, and due to its multi-scale nature, representing physics in the under-resolved scales such as cloud microphysics or turbulence in low resolution climate simulations, as that we call as subgrid scale parameterization, has been a central goal for climate scientists. And here is where we want to get the help from ML, or combine ML and physics-based models to do better on the subgrid scale parameterizations and at all scales. ML has emerged as a promising alternative to SGS parameterization due to its ability to perform equation discovery and its desirable properties as universal function approximators, which do not require prior assumptions about the functional forms of the parameterizations, which means it is physics agnostic. You give it data and it's going to crank out something and say this is what is happening, and then there is the physics in it. Equation discovery is what that is. We summarize recent advances in ML in SGS parameterizations and uncertainty quantification. So I will just touch on these things. Lots of details you will have to read without it. If you will have to read without me if you want to find the details. Without understanding what the ML model actually learns and the reasoning behind it, we cannot deduce when ML model will generalize well into the future climate. So we must understand those things. One approach to improve interpretability is discovering the closed form equations that capture the data. Equations have long been the language for physicists to develop understanding of the systems they govern. With the emergence of ML, ways to comprehend and extract knowledge from ML-based models are new areas of research. Several methods developed to understand what ML model itself learns are detailed in section 4.3, which I am obviously not going to read in detail. So what is machine learning for climate physics then? You have with the increase in availability of data from both observations and high fidelity simulations, these are now a key driver for new physical insights. Below, we introduce two emerging trends of research using ML to improve our understanding of the climate physics using data. One is data-informed knowledge discovery, For example, identifying patterns and dynamical regimes in high-dimensional complex observations and simulations, and secondly, discovering data-informed predictive models. So you jumped the physics there. So data-informed knowledge discovery, we used to use things like EOFs and principal component analysis to get dominant patterns of El Nino with the time series and so on. But now advanced ML techniques emerge as powerful pattern recognition tools that computationally scale well with increasing volumes of data. Off-the-shelf tools widely adopted in climate sciences include supervised learning methods such as random forest, Gaussian process regression, and neural networks, and unsupervised learning methods such as autoencoders and clustering algorithms, so k-means, clustering, self-organization maps, etc. Several of the above tools have been used in climate sciences for decades, long before deep learning took off. So some nomenclatures have changed along the way. What used to be just statistics now gets a bit more complicated, sophisticated with AI ML. Okay, so here we have to worry about dimensionality reduction as well. Climate data often involve high-dimensional, non-linearly correlated spatial and temporal variables such as temperature, pressure, and precipitation across large geographical regions and long time periods. And simple correlations will not allow you to do all this dimensionality reduction, even though PCAs or EOFs have always helped us, especially in large-scale patterns with long time scales such as ENSO. However, traditional techniques such as PCA and EOF have major limitations, such as the lack of a dynamical meaning of the discovered modes and the linearity, because they are statistical features. So here, model uncertainty. Deviation of the physics-based model from the data could be due to inaccurate parameters and physics equations itself. So this is talking about the Lorentz model, which I haven't shown, but you can look it up. And structural errors occur, a type of model uncertainty arising from inaccuracies in the equations used to represent the data or processes of interest. So equation discovery and these things have to go together. So this is a complicated schematic with the Lorentz equation here. So machine learning for climate physics, data-informed knowledge discovery. So dimensionality reduction, basically you have temperature and, let's say, temperature and winds and SST, air temperature, sea surface temperature, pressures, etc. at every grid point, but you don't know what it is, and you do PCA, EOF to get the dominant patterns and time scales, which is dimensionality reductions, and then you figure out the, so PCA, and then you do first PC, second PC. There are often orthogonality constraints and so on. And when you do, that's in the dimensionality reduction. When you do supervised versus unsupervised learning, you have classifications versus clustering with k equal to 2 here. If you don't know that, don't worry about it. Discover ocean dynamical regimes with clustering and physics-based, so physics-informed validation, so you begin to see certain patterns which make sense dynamically, in terms of coupled ocean atmosphere dynamics and responses to anthropogenic forcing and so on and so forth. And data-informed model discovery is got these states with XYZ data, and T is the time, theta are the model parameters that you are trying to derive from the data. So parametric estimation, state estimation, structural estimation, etc. So goals here: discover either parameters or states or mathematical model of F. Mathematical model F. Ensemble-Kalman filter is an example of parametric estimation. Physics-informed neural nets and physics-informed neural operators estimate states, and sparse regression genetic algorithms give you structural estimation of F. Okay, so given x, y, t, z, t at lots of times and mathematical form of the model F. So you have some knowledge that you are trying to fit model too, and so on. So then you want to predict data, which is the ultimate purpose. Of course, you can also be just trying to simulate, and you want to get the state variables and the F form, right? So parameter estimation, uncertainty quantification, and state estimations have to happen, and this is the climate physics part, and then you feed it or take feedback from machine learning for climate simulations, where machine learning for climate simulation again has goals of either doing subgrid scale modeling, machine learning emulators, or physics informed ML. I'm being very brief, but you can do weather forecast from T1 to Ti+1 with an ML emulator, or subgrid scale parameterizations. You want to start, go from data and not want to do high resolution and just do things computationally efficiently with ML based subgrid scale parameterizations in a low resolution model. Okay, I'm being very brief here. Better generalization capacity via incorporating symmetries into neural networks, so you can take physical properties and feed it into ML, into NN neural network, let's say, to generalize the capacity. So here, learn SGS model for subgrid scale modeling, machine learning, discover a model parameterized by ML that best fits given data set, and so on. So I won't go into the details because I'm being lazy, and my idea is to give you an introduction and not go into details. Data informed model discovery. Apart from distilling knowledge from data, physicists have been developing predictive models to describe observations for centuries. So not going into a model, but just use observations themselves to interpret, develop predictions, statistical predictions, you can say. Utility of a model, if it accurately represents the observations, lies in its ability to make predictions when the data is unavailable, such as projections about the future. Not exactly the same. Fitting historical data to a model and doing short-term forecasts versus going into the future as an extrapolation are a little bit different, but approximately the same. Okay, so in this section, model discovery, we mean discovery of mathematical equations. So this is what it is about. Physics informed ML algorithm and its applications in data assimilation, where you are blending data into a model either to do reanalysis or dynamically interpolated gridded data with no gaps in time and space, or you are also going to do initialization for forecasts with assimilation. So you have space and time with hidden layers, as is typical of neural networks, and you have output states. You have mathematical models that you have already formulated either from first principles or, let's say, equation discovery, and inject training. So there is a cost function you are trying to minimize with some data loss and equation loss terms. So you have to check physical consistency and so on. So it's a, you can see it's a multiple iteration loop. You are going back here, coming forward here, and coming forward here, and then you have to also do sparse data inference and inferring non-measurable states, such as glacial ice viscosity for ice sheet models. We don't know what it is. Okay, so we have to infer them from the existing data, reconstruct initial conditions for hurricane forecasts with sparse data. Okay, let me get my tea because I'm feeling, my throat is drying up. I need to drink something, so I'm gonna pause it. Okay, so here is my cup of tea that monsoon has ended. It's fairly dry even though it's warm, so I'm not sure what is bothering me, some sort of an allergy or maybe just some bug that many people seem to be carrying these days. Machine learning for climate simulations. Then we discussed two major directions leveraging ML methods to improve the accuracy of climate simulations. One is, of course, subgrid scale parameterization, aimed at developing more accurate climate models via better representation of small scale which are expensive to resolve by increasing resolution, and they will help physical processes to be captured better, such as clouds and rain, for example. Emulators aimed at generating large ensembles of simulations or directly the statistics at a fraction of the computational cost of a physics-based climate emulation. You do ensembles to basically see what are the potential pathways the future can take. Mother Nature gives you one realization of a weather or a season, but in theory she can go in many directions, and models can tell you what are the different paths Mother Nature could take. Okay, so these two approaches are briefly discussed below. I'm going to be very briefer than their brief. Uncertainties in climate projections. I won't go into details, but basically in the first decade or two, the model uncertainties and internal variabilities dominate. But as you go into longer term, the scenarios that we create, sustainability, bioenergy, carbon capture, transportation and policies, etc., business as usual, fossil fuels, renewable energy, etc., begin to determine the uncertainties in the projections. So, subgrid scale parameterizations, we already talked about it a bit. The process of interest varies on length or time scales smaller than a climate model's resolution, which could be, let's say, 50 kilometers, but obviously clouds are happening at fraction of a kilometer and so on, and equations to describe the processes are not known, such as cloud formations or the interactions of aerosols with clouds and so on and so forth. Okay, so the general idea is to use observations or high resolution simulations to learn a data driven representation or closed form equations of the subgrid scales. Term 2, which I didn't show, examples of the latter approach were discussed before. We mainly focus on neural net approaches. So I'm going to jump forward and talk about climate emulators. Spatiotemporal emulator is an emulator with predictions that evolve with space and time, such as weather forecasting, seasonal forecasting, etc. Initial value problem: a forward model FZ with predictions for zt. So z is the variable you are trying to predict at time t, subject to the initial condition z at t0 specified at time t0, fairly obvious. Boundary value is when, of course, zt is subject to the boundary condition of z at x0 and t, that can be time evolving at the boundaries of x0. In a simple way, ocean is not evolving mostly during weather predictions of a few days, but if you want to go for multiple weeks or seasons, then the ocean also begins to vary. So atmosphere state at every location is affected by the ocean temperatures. So emulator refers to several types of tools in the climate science literature. In general, an emulator is trained to mimic data from physics-based simulations or observations to substantially reduce the computational cost of producing new climate predictions, for example, other climate conditions within the distribution of the training data. So when we keep on saying from physics-based simulations, you can think of it as an analog prediction where you are not going to make real-time predictions, but you will have simulations which hopefully will cover all the possible states that you would expect for any particular thing, like weather or sea ice or extreme events and so on, and you keep the simulations ready and use that as data to train a ML model, so that when you want to make forecasts, you just take the current state observed and you use an analog to say what can happen for either weather or sea ice or cyclone or whatever else. Okay, so I'm being a little brief, but emulators can be used to interpolate the projections from expensive climate simulations, making their projections among different emission scenarios accessible without rerunning the simulations and so on. It remains to be demonstrated that their skill is superior to that of pattern scaling emulators, i.e. emulators that regress regional temperatures on global temperatures or cumulative emissions and so on. But there are already various ML techniques, emulators that are working, such as Climate Bench, and they have been employed to estimate climate impacts of anthropogenic emissions annually up to 2100. So we are doing something that has uncertainties, and now we are saying they are too expensive to keep doing, so we want to use the existing simulations to do it by reduce computational costs, which is a good idea, but then what else gets added to the uncertainties that already exist? So those are the challenges and opportunities of ML-based emulators. Emulators can address the climate response to a particular emission scenario and internal variability, which is the natural variability, and its uncertainty. However, emulators are at best as accurate as the data they are trained on, which may still contain model uncertainty. This may be partially overcome by training with data from very high resolution yet very expensive simulations, such as the emerging global 1 kilometer runs or the K-scale models. Nonetheless, major questions about the stability and physical consistency of the trained spatiotemporal emulators need to be addressed. For example, ML weather forecast models have been shown to produce unstable or unphysical atmospheric circulations beyond 10 days, poorly represent small-scale processes, and do not reproduce the chaotic behavior of weather, which is where the Lorenz model comes in. Potential solutions to address these challenges include incorporating physical constraints into ML models and developing a deeper understanding of the different sources of error and so on. So there are other details such as physics-informed machine learning. So despite ML's ability to emulate weather and parameterize SGS processes, when trained on high-resolution simulations or observations, there is no guarantee that its predictions are physically sound. For example, conservation of mass or energy is not guaranteed by just running ML on data. This physical inconsistency is problematic and makes long-term climate projections using ML-based emulators and ML-based parameterizations not trustworthy. That's where physics-informed ML comes in. Incorporating physics constraints such as conservation laws this is hard. This physical inconsistency is problematic and makes long-term climate projections using ML-based emulators and ML-based parameterizations not trustworthy. Incorporating physics constraints such as conservation laws, symmetries, and more broadly, equivariances, which are defined, which I'm going to skip, has been shown to alleviate a number of challenges such as instabilities and learning in the small data regime. So you can look up this paper who review earlier work in physics-informed ML for weather and climate modeling. So it's great that ML can just learn from the data without knowing any physics, but then it will violate the physics of conservation, for example. Okay, what are the challenges and promises then? Finally, look at epistemic uncertainty. So these are deviations of ML models from the data, could be due to approximation, optimization, and generalization errors. So it's the knowledge creation that itself has uncertainties, and also has spectral biases such as neural networks' tendency to preferentially capture certain frequencies of the training data. So you are going to create biases without knowing what you did in terms of the these are somewhat of black boxes. Answers come out, they look promising, but understanding exactly what happened is always challenging. Okay, so then what are the challenges and promises? Quantifying uncertainties of ML models. Broadly speaking, there are two sources of error in ML-based models: errors in the training data and epistemic uncertainty for the ML model. Errors in the data can stem from sparsity and measurement noise, which are particularly relevant for observations, or from errors in simulation data, which can arise from numerical errors and inaccuracies, inaccurate physics-based equations. The epistemic uncertainty of the ML model arises from different sources such as model architecture and hyperparameters. Some ML techniques such as GPR that we talked about provide rigorous estimates of uncertainty. You can see these these papers. However, for deep learning, uncertainty quantification is more complicated and the subject of extensive research still. Understanding the sources of errors in ML models can improve their stability, physical consistency, and reliability. For example, in simulations coupled with ML-based parameterization, errors from the ML model are propagated into the simulations and vice versa, potentially leading to instabilities and non-physical behavior. Similarly, errors in spatiotemporal emulator can accumulate and destabilize the emulation. Since we cannot directly estimate accuracy during inference, and we do not have access to the ground truth, the best approach is to estimate the uncertainty of the ML model's output, as this uncertainty may be indicative of its accuracy. Here we provide examples from climate science for uncertainty quantification of neural networks, and we also discuss two impactful sources of epistemic uncertainties related to representation error, such as the spectral bias, and data imbalance, such as rare extreme events that may be not well represented. Okay, so here it is: input, output, you have a forward pass, and then you have output and relevance propagation back to the heat map. So you're looking at the North Atlantic. You can look at the details in the paper. I'm obviously being very lazy. So you're looking at wind stress, depth, and sea surface height, and then you are doing forward pass to produce the output globally, and then you are looking at the Atlantic, and then you are feeding it back into relevance propagation to produce heat maps of SSH and so on. This is Thor method, follows fluid dynamics, so you can do feature, so advection, wind and bottom stress, lateral viscosity, some terms are ignored, so nonlinear torque, bottom pressure torque, and so on. Obviously I'm being supremely lazy and superficial, but there are QG turbulence simulations as well. So I'm just going to jump to summary and outlook. Numerous scientific discoveries and rigorous understandings have been driven by empirical relationships. We summarize in section 2.1 how ML can facilitate this, for example, by accelerating the search for patterns in climate data that can be used to derive physical understandings. We also summarized in section 2.2 the premises ML has brought to ML has brought to find closed form equations for poorly understood climate processes. We can look up examples. In many aspects of the climate system, we do not yet have accurate process level models to describe the system, such as sea ice rheology and cloud microphysics. The increasing amount of observational data offers exciting opportunities for both equations and knowledge discovery to improve the fundamental understanding of climate physics. On the other hand, ML can be used as tools to improve simulations. ML models can be coupled with traditional physics-based models and used to parameterize processes for which closed form equations are not yet available, and this is already happening. Radiative model in the GCMs, for example, radiation module. ML has led to breakthroughs in weather forecasting, a task not widely expected to be possible a couple of years ago. Just a couple of years ago, we thought that's not possible. We discussed the challenges to overcome when moving forward from weather forecasting to climate prediction, so stationarity issue and so on. Finally, ML is advancing rapidly, and new techniques and concepts that have shown great promise in other fields are now being quickly adopted in climate science. Notable examples as of this writing include diffusion models, large language models, and foundation models. For a discussion of their design and implementation, and for a downstream task involving gravity waves, look up reference 161. Progress in climate modeling, cloud. It's my lunchtime, I'm so hungry. Progress in climate modeling could greatly benefit from collaborations between the ML, climate sciences, and mathematics communities. For example, the numerical analysis of differential equations and the advent of digital computers played a key role in starting the field of numerical weather and climate prediction, especially there are many specific methods from aerospace engineering, jumps and maxima, minima, monotonicity, etc., were assimilated into weather and climate predictions, and new methods were developed for weather and climate predictions as well, because the physics demands those methods. Developing similar rigorous tools by closely combining the methods from climate physics, ML theory, and numerical analysis can potentially help with building stable, accurate, and trustworthy ML-based models. Okay, so this is fairly long now, 40 minutes. Usually I don't do such long podcasts, but lately I have changed my mode of operation and just doing one long podcast instead of splitting them. Hopefully you are interested enough to listen, or you can skip through these podcasts as you wish. And of course, remember that I'm being supremely brief, and a lot of technical details are quite complicated even for me. So you will have to go back and learn if you are interested in more details. But this should be a good expose for those who are not experts and just trying to get a grasp of what exactly is happening with ML for climate physics improvement, subgrid scale, emulation, predictions, and maybe even projections in the coming years. Okay, see you in the next topic then.